Yes, wonderful. Thank you so much for the introduction, Juniper. So I'll start off with a quick spiel here just before I start sharing my screen as we get into the virtual tour itself. But I'll start with kind of a high level discussion of just the synchrotron and what we might be seeing over the course of this tour. So the CLS is a third generation synchrotron light source user facility. In other words, we are a particle accelerator that uses a beam of relativistic electrons in order to produce very intense, very brilliant beams of light to image samples. At the end of the day, we are, in that sense, a research instrument. And we are used by scientists from Canada and around the world. And really producing light is the name of the game, which is why light source is right there in the name. And on that note, synchrotrons do make for very good light sources. One of the very fundamental properties that we're dealing with here is a phenomenon known as synchrotron radiation. And what synchrotron radiation is when you have a relativistic particle, such as an electron traveling along, and that particle changes its trajectory. So if there is some bend in the path of the electron, that electron will emit light. And that light will continue along in the original direction of travel. And that becomes a very useful tool. And that's really one of the driving phenomenon for why we built the CLS in the first place. And synchrotron radiation is very useful in terms of actually just producing light and having this research instrument, partly because of just the raw amount of photons per second, per unit area, per opening angle, per slice of energy. That's very scientifically useful, but it's also quite nice thanks to the tunability and flexibility of synchrotron light. We produce light across much of the electromagnetic spectrum, whether that's infrared light or soft ultraviolet light, X-ray, even into hard X-ray light. And that broad spectrum makes a synchrotron appealing across many different scientific disciplines, whether it's imaging advanced materials for semiconductors or batteries, or imaging plants and soil samples in agricultural research, biomedical imaging, protein crystallography. All of these different fields of study are things that can get a lot of use out of synchrotron light. Now, there is a lot of work that goes into producing that light, from generating the initial beam of electrons, accelerating and storing those electrons, and all of the different pieces of hardware and controls instrumentation that's used in service of that goal. And those steps, especially what we do with the electrons, is really going to be the focus of tonight's tour. So we're going to follow the accelerator hardware right from the initial generation of an electron pulse all the way through to the storage ring, where electrons circulate and where the photon beams get peeled off for their research. So with that with that little spiel out of the way, I'll begin sharing my screen, and we can start getting into the meat of the tour here. So here we go. Juniper, is this working? Can everyone see my screen okay?
I can.
You can, yes?
Yes.
Okay, wonderful. So what I have done very simply here is I've gone to the main CLS webpage, lightsource.ca, and we have a dedicated page for a virtual tour. So you can see it kind of here initially. And as I scroll down a little bit, we'll get to the tour itself. And I will click go. And so over the course of this tour, I will very much be guiding us along, and I'm sharing my screen. So I'll be controlling where we're looking and pointing out bits of hardware and giving my own description of things along the way. But if anyone is interested in coming back to this tour at some later date, it's freely publicly available on the CLS website. And there are many little bullet points along the way. I won't be paying much attention to these little factoids and bullet points, but if you would like to come back to the tour and review at your own pace, very much you are welcome to. Now, here we go. I'll start going into full screen now. And I will start off with the floor plan before we get too far ahead of ourselves. And this gives us a very quick and broad bird's eye view of the facility itself. So there is a lot to parse and a lot to talk about right off the get-go here. But the main sort of things that I'll be touching on is that electrons will start in the sub-basement of the facility. We have something called an electron gun, which is the hardware used to initially get a beam or a pulse of electrons traveling through a pipe. And following the electron gun, there's a linear accelerator, which is this linear stretch of tunnel here, which will give the electrons a initial boost of acceleration, getting them, making it such that they are relativistic and traveling close to the speed of light. However, there will be more to the story after that. Just as a note, I'm hearing some background chatter, so if whoever that is could mute themselves, that would be appreciated. In any event, once we're at the end of the LINAC, the electron beam will continue traveling along through a transfer line, which is just a beam pipe that will bring the electrons all the way around this bend through to the booster ring, which is the first of our round machines. So the booster ring is itself a synchrotron, and it will, the main purpose of the booster ring, as the name implies, is to boost the electrons up to their final energy. So we will be doing a lot of particle acceleration at this part of the tour. And then eventually the electrons get passed over from the booster ring into the storage ring, which is where any given electron will spend most of its time while it's working for us here in the light source. So once an electron has reached the storage ring, it will be at its full operational energy. And as we get further into the tour, I'll talk a little bit more about what the energy of electron even means. But it will be at its fully accelerated kinetic energy and orbiting around in the storage ring. And as it does that, an electron will be emitting a great deal of synchrotron radiation all along its orbit. And I mentioned earlier that one of the phenomena of synchrotron radiation is that as an electron changes its trajectory, so we can imagine an electron coming along the bend in the storage ring here, it will emit light that continues off in the original direction. So we very frequently get lines of photons or bright beam lines of light that get peeled off of the storage ring tangentially. And because of that behavior of the light getting peeled off of the storage ring in a straight line, that gives the synchrotron a very characteristic sort of shape where we have a central circle and then all of these spokes or all of these beam lines coming off. So each of these different beam lines will have its own beam of light, which it gets to use and steer and focus through various optics to ultimately direct the light onto a scientific sample in an end station in order to conduct some kind of research. And so at any given moment when the synchrotron is on and when normal user operations are underway, we could have dozens of different experiments all unfolding in parallel, unique to one another. So that is a very literal bird's eye view of what we'll be looking at over the course of this tour. And with that, I will now start to teleport us down to the start. And here we are now. All of a sudden, we are in the linear accelerator hall, which is inside of the shielding walls and inside of the tunnel. So we are now looking at actual accelerator hardware, which would be turned on when the machine is turned on. just kind of by coincidence, this month, the machine is presently turned off for a regular planned maintenance outage. So if we were in another world, we could perhaps have people physically in the building to do a tour and be in one of these tunnels. But I suppose life circumstances have forced our hands, and we're doing a virtual tour this time. But fortunately, we have the technology to do it with this tour on the website. So one of the things that we are looking at as we go down, this is the linear accelerator hall. So this is the initial hall where the beam begins. And where the beam really begins is inside of this blue enclosure here, where inside of this is going to be all of the components that comprise the electron gun. So this is the first real stop on the tour. So I'll try to just pan forward a little bit. And here we can get a bit of a view of the electron gun, as well as the high voltage cable and high voltage power supply. So the basic operating principle of the electron gun is it's something that we would call a DC gun. And effectively what happens is inside of this enclosure, there is a small tungsten cathode, or I think a tungsten oxide cathode, which is very similar to the sort of material that you would have in an old incandescent style light bulb. Tungsten being handy because you can kind of pack a lot of electrons or get a lot of electrons out of that kind of material. And that cathode gets heated up very, very hot to about 1,000 degrees Celsius by having a filament running a strong current through just to physically heat it up. And once the tungsten becomes hot, it becomes relatively easy to boil electrons off of the cathode and into free space. And then the one more important step to the gun on top of the cathode and on top of the filament is a high voltage power supply, which we then use to apply a very, very strong voltage to the cathode, which will peel off the electrons, and this electrical voltage, this potential difference, attracts the electrons and gives them an initial kick and sends them on their way out of the gun down the rest of the linac. So with that in mind, I can point out this very, very large diameter cable that is effectively the plug-in for the electron gun. And it gets wound around this large spool on the wall here and works its way into this little enclosure here. And if I back up just a minute, this little pointer here will give us a handy picture, which is, this is letting us peer into the insides of this black container and see the actual components of the high voltage power supply, which is generating 220,000 volts or 220 kV, kilovolts, which is the high voltage power supply for the electron gun. So that's how it all starts. That's how we get our initial pulse of electrons. And the electron gun itself, it won't be firing a continuous beam of electrons. They will come out in pulses. And the overall overarching accelerator hardware, getting the beam from the electron gun all the way into the storage ring, if we are going through that process and accelerating electrons, getting electrons into the storage ring, we would call that an injection. That's just kind of part of the nomenclature at the CLS. And an injection happens over the course of 1 second. So if we were doing an injection and we are sending electrons all the way into the storage ring, the electron gun will be firing at a rate of once per second. So every second, the electron gun fires and another pulse of electrons begins its merry journey. So here is some more of just the early initial hardware. There is some focusing magnets, some solenoids that are used to kind of help shape and guide the electrons as they're emerging from the electron gun, because at this very early stage, the electrons are relatively low in energy, which means that the beam is kind of fuzzy. It's low in energy and it's very easy for it to just sort of diffuse. So we need some hardware early on to help pre-bunch and bunch and guide the electrons along before the acceleration really truly begins, which will start right around here. And the way that the linear accelerator hall is fashioned from a big picture view is we have the electron gun, which is where things start, and then we will have 6 accelerating sections. And each accelerating section is more or less identical and operates under the same principles. So we have this repeating sort of structure of 1, 2, 3, 4, 5, 6 as we go down over the course of this hallway. So I think this is one of my best angles to talk about an accelerating structure. So I'll zoom in on it here, because right now we do have this exposed copper section here. And this is one of the accelerating structures in the LINAC. And if we zoom in even closer and look at the sort of fine vertical lines, we will see that there is a series of these lines. So sort of 1, 2, 3, and they're quite narrow, and there's many of them as we go down along the length of an accelerating section. So this is where a lot of the particle acceleration will happen. And the basic idea, I'll see if it's worth, it might be worth skipping along another step here. Here is yet another accelerating section. This one happens to be covered, but they are, in principle, both accelerating structures. But the way that we will act on the beam and impart more kinetic energy into the electrons is using an electric field. In the case of the electron gun, we just had that DC high voltage power supply that was just a DC acceleration to pull the electrons using this DC voltage and give them an initial kick. But it turns out that DC acceleration really only gets you so far. The kinds of power supplies that you would need in order to accelerate an electron to ultra relativistic energies is just not really feasible. So what we do instead is we will use a time varying electric field, or in other words, a wave. So what we have here inside of this accelerating section is there will be a wave or an electric field that is bouncing back and forth. And the frequency of that wave is lined up with these repeating cavities. So this accelerating section is really a chain or a collection of many cavities, one after the other. And so what happens is this electric field will be oscillating back and forth. At times, it will be traveling in the forward direction, and at other times, it will be traveling in the anti-forward direction. And part of the game for accelerating an electron is we want to synchronize the pulse of electrons that's emerging from this gun and traveling down the LINAC. We want that pulse of electrons to arrive in the accelerating section at the same time as this wave is traveling in the forward direction. So we have this wave going forwards and backwards. And if we can time the electrons correctly, the electrons will arrive as the wave is going in a forward direction, and then the electrons arrive at the crest of this wave, and then the electrons ride along the wave. And at that point, it's extremely synonymous and analogous to a surfer riding along an ocean wave, where the ocean wave is imparting energy and is accelerating and speeding up this surfer, making them go faster. And it's the very much the same sort of principle is applying here, where we ask the electrons to ride along and travel along the crest of this wave, and so become accelerated. And over the course of each of these little cavities, the electron, as it travels along the length of this section, will see a wave, and then it will be handed off to the next cavity, which will again be on crest, and then it will be handed over to the next cavity, and on and on and on. And it will continually see this forward going wave of RF power that it rides along and becomes accelerated in that way. And that's very core to the operation of the synchrotron is using these time varying electric fields and lining up a pulse of electrons to receive a little bit of acceleration and continue on their way. We see that in spades here in the LINAC with these 6 accelerating sections, and we will see a similar story both in the booster ring as well as in the storage ring. So I'm describing this wave and this RF power that's being stored within the accelerating section and how that is being used to impart energy into the electrons. But that RF power, and I guess I should take a quick step back, RF is radio frequency, which is just a quick point of kind of the overall frequency of how quickly this RF wave is bouncing back and forth. The frequency of the linear accelerator is, I want to say, 2856 or 2856 megahertz. So this wave is bouncing back and forth much faster than I can move my mouse, but I think you get the idea. And this RF power needs to come from somewhere. And if we look at the machine, we can make a judgment as to where that RF power is actually coming from. We can see something called a waveguide here that's traveling along above the electron beam pipe, and eventually it connects up to this accelerating section here. And if I pan slowly, we will probably see the waveguide possibly for the next accelerating section as well. There we go. We end up seeing the waveguide for the previous section, as well as the waveguide for this section down here. And a waveguide is really just a special sort of pipe that has a well-defined cross-section. And the cross-section of this pipe is well optimized in order to allow the RF power to move through the waveguide with a minimal amount of losses along the way. And these two waveguides will both end up going upwards and disappearing into the ceiling. We can't quite see where they disappear because there's a cable tray blocking our field of view right now. But these waveguides will go up and out of the room. And on the other end, into a higher level in the facility, the next floor up, there's something called the modulator room. And the modulators are another kind of hardware. We won't physically look at them here in the tour, but they are where the RF power for the linear accelerator gets generated, it gets amplified, and once it's ready, the RF power gets sent out from the modulators and through these waveguides down here to where the RF power gets used here in the LINAC. So that is a lot of the main pieces of hardware here in the linear accelerator. There will be, of course, some other sort of diagnostic and basic infrastructure kind of things, like we will have some vacuum pumps along the way. I'll see if I can find a good angle of a vacuum pump. Oh boy. There will also be view screens. View screens are something that we'll use quite often in the control room in order to image the beam. There's just a sort of basic phosphorescent or fluorescent screen that gets run in. And once the view screen is in place, an electron pulse traveling down the LINAC will go through the screen and cause a flash. which allows us to get a sense of the position and size of the beam at various points along the course of the linac, which is helpful if we're doing any kind of diagnostics or I guess setting up the linac itself. But during general use, the view screens would be out, since when they're in, it's a bit of a destructive measurement, you could say. But here's a little bit of infrastructure here. You'll be seeing along the way, especially if you come back to the tour, lots of devices that have the label IOP. That's an ion pump. So that's a particular kind or a special kind of vacuum pump that's specific to ultra high vacuum scenarios. Like you won't really see an ion pump acting under atmospheric pressures. Ion pumps don't work very well when the pressure is close to what you and I are feeling right now. But the vacuum level inside of the electron beam pipe is very, very low. It tends to be on the order of e to the minus 10 or e to the minus 9, e to the minus, sometimes we don't really get down to the minus 11s, but usually to the minus 9, minus 10 of torr. And let's see, I didn't quite do my homework. I don't quite remember offhand how much torr is atmospheric pressure. I want to say a few hundred, maybe several hundred, but there's plenty of engineers on the call here. So if I'm wrong, I imagine someone could correct me. But here we have another accelerating section. We've got a pretty good view here of the different cavities, so you can get a sense for the span over which the RF power, that wave is sloshing back and forth inside each of these cavities. There's another up close view of a waveguide. And as we continue along past our 6 accelerating sections, fairly shortly here, we will arrive at the end of the linear accelerator. And as we get to the end of the linear accelerator, I can take a bit of time to talk more about the kinetic energy of the beam. So at the start with the electron gun, we had that 220 kilovolt DC high voltage power supply. So that was imparting 220,000 volts of acceleration to an electron. And if an electron gets pulled from, let's say, ground, and it sees a 1 voltage potential voltage that pulls it along from ground over to 1 volt, it receives some energy from that potential difference. And an electron traveling through 1 volt of potential energy gives that electron 1 electron volt of energy. The electron volt is a handy unit that shows up fairly frequently in undergraduate physics problems, and it also gets plenty of use here at the synchrotron. So if we're talking about just in terms of electron volts, that you kind of need to do a little bit of conversion in your head to actually think, an electron volt is a unit of energy, but it's also being used as a metric for how fast or how much kinetic energy an electron has. And that unit just sort of becomes commonplace in the vernacular at a synchrotron. But I'll do a couple of quick conversions here for us here. So an electron at the end of the electron gun has 220,000 electron volts of energy, and that works out to roughly 70% of the speed of light is kind of the actual velocity of the electron right at the very start coming out of the gun. Now that we're here at the end of the linac, these 6 accelerating sections will together accelerate the electrons up to an energy of 250 million electron volts, or 250 MeV, mega electron volts. And at that much energy, the electrons are traveling at 99.999% of the speed of light, or 5 nines. So they're really quite a relativistic at this point. They're traveling very, very close to the speed of light. Of course, we can't identically reach the speed of light or surpass the speed of light, but we can get pretty darn close. And this 250 mega electron volts, this will be the energy at which the electrons are traveling for the next while. Now that we're at the end of the linear accelerator, we're done with particle acceleration for the short term. But our next main destination on the tour will be following the electrons along the way to the booster ring. And once the electrons get to the booster ring, that's when we will do some more acceleration. We'll bring the electrons up to their final destination of 2.9 billion with a B electron volts, or 2.9 giga electron volts. And once the electrons reach that energy, they will be traveling at 99.99999% of the speed of light. We will have arrived at 7 nines. And 2.9, or you could just round and call it 3 giga electron volts is a very popular energy for synchrotron light sources, or electron synchrotron light source machines. There's a lot of machines around the world that operate at this energy, and it tends to be just a bit of a Goldilocks zone. Once electrons are operating at that energy, that's this sweet spot for getting light in the infrared spectrum, in the ultraviolet spectrum, in the hard X-ray spectrum. It's just a nice operating point for producing different kinds of light across different kinds of energy ranges.
So if I can quickly interject, we have a question. What is the purpose of those cavities in the accelerator sections?
Sure thing. So the cavities in the accelerating sections. Here's a nice sidelong view. Inside of each and every one of these cavities, there will be a wave or an electric field that is oscillating back and forth. And the cavity is specifically shaped in order to contain this RF power, or this electric field, and allow that wave to oscillate back and forth with minimal losses. So we can efficiently store this power inside of this cavity. And in that way, the cavity houses this electric field as it oscillates back and forth. And that is a core necessity to accelerating the beam, because once we have this cavity and we have this electric field bouncing back and forth, or sloshing back and forth, since it's a wave, we will have a pulse of electrons traveling along the linac, and the phase, or the timing of the electric field inside each of these cavities is synchronized such that the electron is always finding the positive crest of this wave as it's bouncing back and forth. So each time an electron arrives at this cavity, it will see the electric field traveling in the same direction as the electron wants to go, and it will get a little bit of a boost. And then it arrives at the next cavity and it gets a little bit of a boost, and a little bit of a boost, and a little bit of a boost. So the cavities are this physical hardware, physical structure that we use to contain the power used to accelerate the beam. And I am about to move on from the linac. So if there are any other questions, Juniper, feel free to flag me down, and I can pause here. If not, I will keep going. And it's easy enough for us to circle back to questions at the end as well. So here we are at the end of the last of the accelerating sections in the linac, and we're looking at something that is a little bit covered up in some radiation shielding. And what we are physically looking at is something called a beam stop, which will just literally be a piece of hardware, or like a kind of a copper plate that we can physically run into to the beam pipe, and it would interrupt the beam of electrons from traveling any further. And these sorts of beam stops are a convenient piece of hardware that we can use in order to isolate different sections of the accelerator chain from one another. For example, it's not that unusual to, during a shift, just try and tune up the performance of the linear accelerator. We might be adjusting the timing of those waves along each of the 6 accelerating sections. Or there might be some small steering magnets that I didn't quite point out, but I'll get to steering magnets soon, that can be used to kind of optimize the position of the electron beam. And we might only be interested in optimizing the beam through the LINAC without necessarily spraying electrons further down. And the beam stop becomes this nice convenient way of just terminating the beam in a well-controlled fashion. But most of the time, if we're operating the machine, the beam stops will be open, and that will allow the beam to travel all the way end to end. So now, here we are at the end of the accelerating section. I've been talking about electric fields or RF power and how that's used to accelerate the beam. But another thing, or another concept that we will really be seeing plentifully throughout the tour here, is magnets and magnetic fields. In a very short summary kind of way, electric fields are great for accelerating a particle because the electric field can travel in that same kind of parallel direction as the beam, and so give it a boost. And by the same token, magnetic fields are very good for steering the beam or applying a force that is perpendicular to the travel of the beam. And one of the very most basic sorts of magnets in this application is a dipole magnet. We're looking at 3 large dipole magnets here. Mostly we're just seeing kind of the outer shells, but I'll try to zoom in. It will be easier once we get to the other sides of the magnets. But the basic idea is that there is a laminated coil of wire, one coil being above the electron beam pipe and another coil of wire being below the electron beam pipe. And each of these coils is energized with a lot of current that comes from a power supply. And by sending an electrical current through a coil, you can generate a magnetic field. And by having 2 symmetric coils, you can generate a magnetic field that is constant and uniform, that travels from one coil to the next coil. So right now we're generating a vertical magnetic field in each of these 3 magnets. And because of the right-hand rule, as we have a electron traveling from side to side, from the right part of the screen to the left part of the screen, and we have a vertical magnetic field, the resulting force upon that electron is in the horizontal plane. So we have here 3 large horizontal steering magnets. And we can, depth perception is a little bit hard in this view here, but we can see one beam pipe that's going directly from the first magnet over to the third magnet. This beam pipe here, this B301, this section, 99% of the time will not see any electrons. Electrons will only travel through this particular section of pipe if this magnet right at the very foreground of the screen is turned off. If this magnet is turned off, it will not apply any steering and the beam will continue straight through. But most of the time, these 3 magnets are on, and what they end up doing is they steer the beam kind of back and forth and straight again in this little triangle of bends, which might seem like it adds up to nothing if we just steer one way, steer the other way, and straighten out again. But something that's important to note here is the more energy an electron has, that will effectively how the electron takes the corner as it travels through the bending field of a dipole magnet. If an electron has a little bit more energy and is traveling that much closer to the speed of light, it will have a narrower bend as it travels through a dipole magnet as compared to an electron that has a comparatively low amount of energy, which would then experience a stronger bending angle from the dipole. So with these three bending magnets in a row, what that effectively does is electrons that have more energy will take these three corners more sharply, and they will come out ahead. And electrons that have less energy will be bent more strongly, and they will start to lag behind. So we can take any amount of energy spread within the pulse of electrons that has reached the end of the LINAC and cause that energy spread to be translated into a spatial spread, where we will spatially spread out the electron beam based on the energy of those particles. And that becomes helpful if we then immediately act on the electrons that have been spread out according to their energy, and give the electrons that have too much energy, make them pay a little bit of a toll and slow down a little bit, and the electrons that are trailing the pack that have a little bit less energy, give them a little bit of an extra boost so that they can catch up. And in that way, we can improve the quality of our beam by making the electrons within this pulse have a more uniform energy. And that little toll and boost system ends up happening in this hardware here. There's just a very small additional accelerating section that's placed at the end of those three magnets, which are now at the other end of this shielding wall. And this entire system with the three bend magnets and the final accelerating section is something that we call the ECS, or the energy compression system. And its purpose is exactly what I described, of just improving the quality and the energy spread of the beam. Now that we've arrived at this large room here, we are officially at the end of the linear accelerator. The LINAC is behind us, and we have reached a new section of the machine. And the purpose of this section is fairly simple. There isn't any accelerating happening, as I mentioned before, where we're done with accelerating sections for the time being. But now, very simply, we need to get the electrons from where they are to the booster ring, because the booster ring is the next link in the chain where we will finish the acceleration of the electrons. But first, we just need to physically get them there. And that's the purpose of this part of the machine, which is called the transfer line. We call it the LINAC to booster transfer line, or the LTB for short. And effectively, what we will see over the course of the LTB is a lot of beam pipe and a lot of magnets. I've already talked a bit about dipole magnets. I'll see if I can find a good view. This is a pretty good view of a dipole magnet here as we're looking. We can see a large iron yoke. This metal here is used to kind of shape and channel magnetic flux lines, or magnetic flux, which is initially generated by the two current carrying coils. And again, the idea here is to just generate a nice uniform vertical magnetic field that will apply horizontal steering to the beam. So that is a dipole magnet. We'll be seeing a lot of these as we continue on, of various shapes and sizes. And another very fundamental, very important kind of magnet is the quadrupole magnet. And here we can see a nice string of them here. And I'll choose to zoom in on this one because we've got a pretty reasonable angle. And the defining characteristic of a quadrupole magnet is that we have these 4 symmetric coils positioned about the electron beam pipe. And then a power supply would energize these coils with a current, and that will generate a magnetic field. And based on the symmetry of the positioning of these coils, if we were to look at the very, very horizontal and vertical center of this quadrupole magnet, we would not see any magnetic field at all. The 4 coils would cancel themselves out. So we don't get any magnetic field at the very center of the quadrupole magnet. But as you travel, either veering off to the left or right horizontally or up and down vertically, you will get closer to 1 or 2 of the coils, and you will gradually, in a linear fashion, get a stronger and stronger magnetic field. So what a quadrupole ends up doing is it behaves a whole lot like a focusing lens. So we can kind of think of the electron beam in optical terms, where if we were to do nothing and just spray the electron beam down the beam pipe, eventually those electrons would diffuse and disperse, and the transverse size or the waist of this beam would expand and expand, and eventually the electrons would just be lost as they scrape against the outer vacuum chamber. So it's very important that we use these quadrupole magnets to act on the electron beam and focus it back down so that we can maintain a nice tight beam spot. We want the beam to be well focused and is really as small as we can realistically achieve, because after all, we're a light source, and the size of the electron beam will ultimately have an influence on the size of the photon beam. So if we want to generate a nice focused beam of light for scientists to conduct their experiments and image their samples, it's important that we have a fine degree of control over the electron beam and ensure that we get a nice high quality beam by focusing it down. And one of the quirks of physics has the result that a quadrupole magnet can only focus in one plane at a time. So if any one of these quadrupole magnets happens to be focusing the beam in the horizontal plane and bringing the beam down horizontally, that same quadrupole magnet will be defocusing the beam in the vertical plane. And that's just sort of a quirk of Maxwell's equations. There isn't really any getting away from that. But operationally, something that we can do is group these quadrupoles together. Very often they're grouped 2 by 2 in this so-called quadrupole doublet. And what that allows you to do is, let's just say initially you focus the beam down horizontally. So you're focusing the beam. This first magnet is taking the beam and trying to focus it down horizontally at the cost of defocusing it vertically. Then, once we get to the second magnet, the electron beam will be nice and tight horizontally and maybe a little bit smeared out vertically. But if the beam is nice and tight horizontally, it's close to traveling through the center of this quadrupole. So it's close to not seeing any field at all. So it will not suffer that much from the horizontal defocusing effect of the magnet. And it will benefit a lot with its relatively vertically smeared out beam. It will benefit a lot from the vertical focusing of this beam. So the quadrupole doublet, with having first focusing the beam in one plane and then focusing the beam in the other plane while it's already focused in the first plane, this is very much a 2 heads is better than 1 kind of scenario, where you achieve net focusing despite the limitations of what equations in a physics textbook might tell you. So we see a lot of dipole magnets. We see a lot of quadrupole magnets. I'll continue to point them out as we go along the tour. And there will also be some smaller magnets along the way. I won't worry too much about what's immediately ahead of us. So we can continue along through this first room of the LTV transfer line. And while I've got a nice bird's eye view here, I'll take a moment to talk about one of the safety systems or one of the safety protocols that we have at the CLS. Because of course, if we were physically in this room right now, the machine would have to be off. If the machine were on and there were accelerated electrons traveling through the beam pipe, this room would not be safe for personnel. Synchrotron radiation is immensely useful as a light source, but radiation is radiation, and that is a hazard that we need to treat seriously at the CLS, and we do need to have safety protocols. One of the protocols that we have is the process of locking up a zone. And when I say zone, I specifically mean a part of the facility that is within the shielding walls. It's inside the accelerator complex. And by locking up, I mean 2 lockup inspectors will go into the zone. And as they lock up the zone, they will confirm that they are the last 2 people to exit that zone. And they will exit through a specific and unique door. Each zone only has 1 point of access. And once the lockup inspectors leave the zone, they will lock the way behind them, and they will know that they were the last 2 people out because they did an inspection to make sure there wasn't anyone else in the room. And then they lock the way behind them. And in that fashion, we know that a zone is empty of personnel. And one of the ways in which lockup inspectors convince themselves that they're the last people to exit the room is that they need to follow a prescribed path that guides them through the entirety of the zone. And as they're following along this path, they're looking around for anyone else who might be in the room. And that path gets dictated by these little lockup stations that are positioned along the wall. So if someone is locking up a zone, they need to go to each of these stations and push a physical button on it. And the reason I'm bringing this up is there are 4 or 5 of these lockup stations within this room. And while we're here in this bird's eye view, we can see a great many of them. And we can even see the numbers, which is telling us the order in which these lockup stations get pressed. So there's one there, there's another one there. And if I pan over, we'll see another one at the far side of the room there. So that protocol of locking up a zone is part of our access control, and that's a regular part of both turning off and turning on the machine. If we're at the end of a maintenance outage and it's time to turn the machine back on, we need to lock up all the zones and make sure that it's safe to proceed. So here we're seeing a 90-degree bend, which is actually a first. We were seeing some bends with that initial ECS, but now we've got a series of dipole magnets, and each dipole will partially bend the beam. And as we add that up, magnet by magnet, eventually we get a nice 90-degree turn in the electron beam path. And again, this is just a physical necessity of getting the electrons from A to B. And I could take a quick moment to kind of talk about the history of the machine. The LINAC is, of course, rather old hardware. It's positioned here in this sub-basement. And a lot of the components of the linear accelerator actually predate the rest of the synchrotron. Before the CLS was the CLS, there was something called the SAL, or the Saskatchewan Accelerator Laboratory, where nuclear physics and various experiments were done. And the SAL had a LINAC. They had this LINAC. Some components of the LINAC have since been replaced just with kind of newer replacement spares, but the history of the facility goes back quite a long ways. And that then kind of ricochets into these little consequences of needing a particularly long transfer line to get from the LINAC, which was already here, to the booster ring, which is where we're going. Here is another example of a beam stop. This here is a shielding along the LTB, along the transfer line. So there is a beam stop that is well hidden and well buried by this little fortress of shielding blocks. And this particular beam stop allows us to prevent the beam from traveling further down into the booster ring, while at the same time, if we would like to have beam traveling along the LINAC to well optimize it and maybe check different diagnostic view screens and see that the beam is well steered as it travels through the LTB up until this point, that's something that we might do just as a matter of course. Here, we're about to be done with the sub-basement part of the facility. So we do actually need to change the vertical position and the vertical plane of the electron beam. And the natural way that we can do that is again with the dipole magnet to steer the beam. But this time, since we're vertically steering the beam rather than horizontally, we need to rotate our dipole magnet 90 degrees. So here we have a vertical steering dipole magnet where the coils have just been rotated 90 degrees like that. And of course, since these are large coils with large power supplies with large currents, it's not really sufficient to just let those magnets be cooled off with air. We do actually need water cooling lines to keep the magnet cool. So it's pretty frequent that you will see these orange lines for water cooling hooked up to magnets. On and on we go. Here at this point, I'll take a little moment to point out more shielding bricks. Most of the shielding bricks that we have at the CLS will be color-coded based on their function. And often we will see either yellow or blue. The two colors dictate the purpose. So what is the shielding protecting? Blue will be protecting any kind of sensitive mechanical hardware that might need protection from just the ambient radiation of electrons zipping along with the machine on. So we could have blue shielding to protect components. And on the other hand, we will also have yellow components to protect personnel. So with this particular example, we have yet another vertical dipole, which is steering the beam and straightening it out so that it's once again traveling level to ground. But at this point, the electrons are fairly relativistic, and if we're changing their trajectory, they're going to emit synchrotron radiation, like it or not. And in this case, synchrotron radiation would continue to spray in that original path. So we could be spraying radiation up into the ceiling here and maybe into some other room within the light source facility. So it's important to just lay down some shielding bricks right at the source point and control any radiation that might be coming off of this dipole magnet. Once again, as we travel along, we've got another doublet of quadrupoles side by side. And we also have a much smaller magnet here, which we'll start to see more and more of as we proceed along the machine. And we can see one of the coils here facing us. It's a little bit tough to see with the angle, but there'll be a coil. There's basically a total of 4 coils along the cardinal directions, left, right, above, below of this beam pipe. And those windings will be hooked up to a power supply, and that power supply can be given some variable set point. And this is a very small magnet, but it is 2 dipole magnets, let's say. There is both a horizontal dipole and a vertical dipole. So we can apply both horizontal steering as well as vertical steering with this small little magnet. Of course, since it's a much smaller magnet compared to the ones we've been seeing before, the amount of bend that can be applied to the beam with this small magnet is much, much smaller. So it's not the sort of magnets that will allow us to get a big 90-degree bend in the beam, but it will allow us to apply some small correction or some fine tuning. Maybe if we look at a nearby view screen, I'm not sure where the nearest view screen is here, but if we were to image the beam at some point along the transfer line and compare the pulse of the beam compared to some reference image, maybe we can see that the beam is just a little high and a little to the right compared to our reference capture of where we want the beam to be if it's well behaved and traveling through the transfer line. We wouldn't necessarily change the set point of these large magnets, but we could, just as a matter of routine, update the set points of these small steering magnets just to optimize how the beam is traveling through the accelerator chain. So here we are traveling along the home stretch of the transfer line, and we are very close to arriving at the next major part of the machine. Up the ladder and through the gate, again seeing more of these little lockup stations all along the way. And as we arrive here, we are now entering into the tunnel of the booster ring. So the booster ring is the first of the two synchrotrons at the Canadian light source. Both the booster ring as well as the storage ring are technically synchrotrons by their shape and by their function. However, the CLS uses both of them together, and the storage ring is, of course, where the electrons are stored for a long period of time, and the storage ring is where we are actually concerned with making use of synchrotron radiation as the electrons zip around. Synchrotron radiation will be produced as the electrons are getting bent and steered and moved through the LINAC, through the transfer line, through the booster ring. But that synchrotron radiation is really just a byproduct, and it's not necessarily something that we're going to use for an experimental beamline. So here we are, and we can see the transfer line. There are some more dipole magnets and some more yellow shielding bricks bending the beam along. If this particular dipole magnet were off, the beam would travel straight through rather than be bent, and it would go along this little line here and swiftly be terminated. We might have some diagnostics along this very, very brief line, but most of the time this won't be used. Instead, the electrons will be steered along down that line into the background, and you can start to see just in the center of the frame here, the transfer line sync up with the booster ring. And I'll come at this from the other end in just a minute, but we can see how those two beam pipes will eventually converge. Now, the booster ring is a very important part of the chain, because this is where we take the electrons, which at present have 250 mega electron volts of energy, and we need to bring them the rest of the way up to 2.9 billion electron volts. And the way that we do that is we allow the electrons to circulate around in the booster ring many, many times. I think it's about 1.5 million turns over the course of 600 milliseconds. And over that time, a pulse of electrons, so a single shot from the gun traveling through the LINAC, through the LTB, and into this booster ring here, they'll orbit around. And as they are doing that, each pass the electrons make around the booster ring, they will be traveling through this section here. And this section is a little bit larger than the 6 sections we were looking at earlier in the tour when we were traveling along the LINAC, but it's the same basic idea. This is a RF cavity. It's a much larger cavity than what we were looking at before, but it's the same basic idea of it being a cavity in which we are storing RF power. And that RF power will be in each of these little sections be zipping back and forth. And we will synchronize our electrons as they circulate around the booster ring to line up with the positive crest to receive a positive kick and a longitudinal kick that will impart more energy and allow the electrons to travel at a higher velocity, thanks to this accelerating electric field. And because the booster ring it's not a perfect circle, but we would just call it a circular machine because it's not a linear machine. It has this closed path. The electrons will circle around, and as they go, each pass, they will come around to this RF cavity again and again, and they will receive more acceleration and again. So we can get a lot of use out of this booster ring cavity and accelerate the electrons upwards in energy. And that is how we will arrive at our final destination of 2.9 giga electron volts. Now, another thing that I can point out, which kind of circles back to what I was talking about earlier with the ECS, or the energy compression system that was at the end of the LINAC. Remember that the energy of an electron dictates how strongly it is or is not affected by the bending force of a dipole magnet. So we have these dipole magnets, and I'll actually change my vantage so that we get a better view of the booster ring magnets. Here we can really see the structure of the booster ring as it disappears around the corner. We've got a lot of these dipole magnets that are being used to bend the electron beam and close the orbit into this roughly circular path. But if the electrons are getting accelerated more and more and getting more and more energy, they will be affected less and less by the field strength of a dipole. So the entire booster ring, it is important that the strength of the magnetic fields of all of these components along the booster ring also increase, such that the bending strength of the dipoles keeps pace with the increasing energy of the electron beam. And this is something that has to happen quite quickly. I mentioned that the electrons are only in the booster ring for a little more than half a second. And this is something that we call the ramp of the booster ring. So the entire booster ring has a 1 second ramp, since the electron gun is scheduled to fire once a second while we're going through the process of filling up the storage ring with new current. And over the course of that 1 second ramp, all of the power supplies for all of the booster ring dipoles and quadrupoles need to start at the set point that is appropriate for 250 mega electron volt energy and ramp up in time with the electrons as they're accelerating and making their way up to 2.9 billion electron volt energy. And then the set points need to ramp all the way back down to reset, because of course, if the magnets are dialed in for a fully accelerated beam and a new beam comes along that hasn't yet been accelerated, that beam will not stand a chance. It will immediately be lost as the dipoles bend it too strongly and just shoot it into the beam pipe. So the booster ring, at a glance, seems, I don't know if people will disagree with me, but a little simple in the sense that it has the RF cavity and it has the magnets, the dipoles and the quadrupoles, and that's most of the story to the booster ring. But those components, they need to go through the course of this ramp in order to meet the electrons halfway and keep up with the acceleration and the large change in beam energy as the electrons spend their very brief stay in the booster ring. There is another important piece of hardware in the booster ring. Most of it is hidden away inside of this danger high voltage enclosure, but it is an important piece to the story. And it's something called a kicker magnet. We will be seeing more of these kicker magnets as the tour goes on, but this is our first one. And the basic idea of a kicker magnet is it's similar to a dipole magnet in the sense that it is applying steering to the beam, except whereas a dipole magnet is this steady state DC fixed magnetic field, with the exception of the booster ring ramp. The kicker magnet is a much, much faster sort of beast. Rather than a electromagnet, it is this fast pulsed power supply that will, over the course of maybe even hundreds of nanoseconds, a very short pulse will just fire. And the kind of analog or metaphor for what a kicker magnet really behaves like is it's similar to the switchyard in a railroad track. So if the kickers do not fire, the electrons will travel along their initial path. But then if the kickers do fire, the electrons very suddenly get course corrected and they will now travel along a different path. So this kicker in particular, it is the booster ring injection kicker, and its job is to straighten out the electrons that are coming in from the LINAC to booster transfer line. So if this kicker didn't fire, electrons would come in from the transfer line and they'd be coming in way off position and way off angle, and they wouldn't be well prepared to circulate in the booster ring. And they might swerve around a bit as they travel through one dipole and then the next dipole, but pretty quickly they would become lost either by striking the beam chamber or what have you. So it's important for this kicker magnet to fire and straighten out the trajectory. And we will similarly see kickers wherever we have the interfaces between different sections of the accelerator hardware. So there will be another kicker to extract beam from the booster ring, and there will be more kickers to inject beam into the storage ring. So as we go along the booster ring here, we will very quickly and very apparently see that it is a repetitive sort of machine. One of the things that we talk about with a synchrotron is what is the lattice structure. And we borrow the word lattice from crystals, where crystals have this regular repeating atomic structure. There is a crystal lattice. There is also a lattice to synchrotron machines. And the lattice for our booster ring is really as simple as it can be, where we have a quadrupole magnet, we have a dipole magnet, we have another quadrupole magnet. And that sort of section will just repeat itself around the length of the whole ring. And really all that we need to worry about, similarly to the transfer line, is we need to worry about keeping the beam nice and focused. So we have these quadrupole magnets in order to act on the width and the waist of the beam to focus it down and keep a nice tight beam spot. And then we have these dipoles in order to steer the beam and close the orbit. And sometimes along the way, we might see some corrector magnets, which are just really those smaller steering dipole magnets, which are not meant for strong bends, but rather for fine tuning. Some of the other hardware that we'll see along the way is more of those ion pumps to maintain good vacuum, as well as cold cathode gauges, which is the devices we typically use to measure vacuum at this light source. And we will also have some diagnostic view screens here and there. And I'm trying to decide if that's a vacuum valve that we're looking at right now. Well, it's behind us now. We will also see some vacuum valves that are important in order to potentially quarantine off different sections of the ring. For example, if we were to spring a leak, or if something were to outgas suddenly and abruptly vent part of the booster ring or part of the storage ring to atmospheric pressure, a cold cathode gauge would detect that. It would see the sudden spike in vacuum levels, and then the next nearest vacuum valves would automatically close themselves very quickly in order to isolate any possible bad vacuum that gets detected. But as I'm saying that, well, I don't have a good enough view of that particular component to see if it's a vacuum valve, but shortly enough I will see a valve and I'll point it out for everyone. There is a corrector magnet. Typically these will be colored yellow, and they've got the label of OC for orbit corrector, and then either OCH as a horizontal magnet or a OCV for a vertical corrector magnet. They're much smaller relative to the dipole magnets, as I've mentioned. And of course, we'll have some water cooling lines. We'll have electrical cable trays below and more cable trays below. There's a lot of kind of supporting infrastructure that needs to be in place to keep these magnets operating, and the various beam diagnostics as well. And as we round the bend here, we can see the booster extraction kicker up ahead. So we're getting close to the end of our time here with the beam and the booster ring, and we're just about ready for the final stop of the tour, which will be the storage ring. And I believe I can take a bit of a shortcut with this part of the tour. Normally, if we were walking around in the tunnels, we'd have to physically finagle our way from one tunneling wall over to the other tunneling wall. But at the time this tour was taken, or yeah, at the time the pictures for this virtual tour were taken, the machine was in shutdown for maintenance mode. And often, but not always, when the machine is in maintenance mode, the tunnel walls, the shielding walls that separate the booster ring from the storage ring, sometimes those tunnel walls get opened up just for easier access. And that was done here. So I'm cautiously optimistic that if I click, I can make my way over to the storage ring. So bear with me. There we go, magic. So now we're on the other side of the booster ring. Just a little bit further upstream was the booster extraction kicker. And we've got a okay angle here to actually talk about the booster to storage transfer line. Similarly to how we needed to move the beam from the LINAC to the booster ring, there was that LTB transfer line. There is also a transfer line that needs to shepherd the beam from the booster ring to the storage ring. This transfer line is of course much shorter than the LTB was, because there is less physical separation between the storage ring, which we can glimpse just over on the left side of my frame, and the booster ring, which is over here. But as we move further downstream from that booster extraction kicker, what ends up happening is if the booster extraction kicker fires with that very quick pulse, the electrons see the change in the switchyard and they realize that they're on a new trajectory now, and they will no longer travel along the trajectory or the orbit of the booster ring. Instead, they'll gradually diverge from this angle in their trajectory and find their way instead down the booster to storage ring transfer line. And this transfer line is again similar to the previous transfer line, a combination of dipole magnets and quadrupole magnets and small orbit corrector steering magnets. And the steering magnets in particular are quite important in this section of the machine, because we want to be as efficient as we realistically can with moving electrons from the booster ring into the storage ring. We want to have as high of a capture efficiency as we can manage, because if we don't capture the electrons, instead we lose the electrons. And if the electrons get lost, well, they're highly accelerated particles, so they might be causing some Bremsstrahlung radiation if they hit the shielding wall, or other forms of synchrotron radiation as they get steered and moved about. So if any injection losses are effectively radiation that we don't need or want. And for the most part, that radiation is very well controlled and shielded by the tunneling wall, by the walls of the tunnel. But the higher our injection efficiency, the lower our ambient radiation around the facility. And that's just good practice in terms of keeping radiation as low as reasonably achievable, or ALARA is one of the short metrics that we have when we talk about radiation safety. So if I step through the tunnel wall here, we can make our way into the storage ring, and immediately, right at first glance, you can perhaps detect that the storage ring has more going on than the booster ring. Previously, we just had that very simple repeating lattice structure of magnets with dipole, quadrupole, dipole, quadrupole. Now, the storage ring lattice is more involved. And we have something that we might call the cell, or the one string of magnets that will repeat over and over again. The storage ring has 12-fold symmetry, so we'll see 12 of these cells if we were to walk a full lap around the storage ring. And the way that a cell looks is there's two initial quadrupoles, there's the first dipole, there's a series of quadrupoles and a new red color of magnet that I'll talk about soon, and then a second dipole and two final quadrupoles to close it out. And so we will see this repeating structure many times as we go around the storage ring. And it's also worth noting that this one cell has two dipoles. And because of that, we would call this a double bend acromat. That's kind of the jargon for describing the overall shape of the CLS storage ring. There's a lot of double bend acromat type machines around the world, but as the technology and the understanding and the technical capability and the budgets of synchrotrons improve around the world, we're starting to collectively as a community make the jump from so-called third generation light sources, which is what we have in Canada, to fourth generation machines or next generation machines. And one of the things that is different about a next generation machine compared to the one that we have now is, instead of having something like a double bend or a triple bend acromat, you might have this multi-bend acromat, where instead of having just two, you might have 5 or 6 or 7 dipole magnets in this section. And in a quick sort of explanation for why you might do that, by increasing the number of bends kind of per unit area or unit section of the storage ring, you are also applying smaller bends, because effectively you want to get to 360 degrees of total bend in order to have a closed orbit in your machine. And you can do that with 24 bends if you have 2 bends across 12 sections like we do at CLS, or you could do that in a much higher number than 24. And instead of 360 degrees divided by 24 bends, it might be divided by a much larger number by applying a much smaller bend. And if you think it through, applying more smaller bends is just innately kind of more gentle on the beam. Rather than having a loony with sharp corners, you're gradually rounding that down. And as you do that and apply increasingly gentler and gentler bends to the beam with a larger and larger number of dipoles, you can achieve overall a smaller electron beam size. And that's one of the ways in which the design of synchrotrons and the realization of synchrotrons has improved over, say, the past couple of decades. But I say decades, but that's in terms of design. Fourth generation machines are really quite new, and there are only a couple of them coming online around the world these days. Okay, that was a bit of a tangent, but as we talk about the storage ring and the beam circulating around here in the storage ring, As I've mentioned previously, this is where the electrons spend most of their time, and this is where we extract most of our use from them. This is where electrons will be producing synchrotron radiation in meaningful amounts and in meaningful locations. And that synchrotron radiation, as it gets peeled off of the storage ring, it will be peeled off as beams of photons, and those brilliant, well-focused beams of photons will zip their way down to an experimental end station. So, as I just pointed out, our lattice structure, our cell, consists of 2 dipoles per section. Each of these dipoles is the potential source point for a beamline and for an experimental end station at the CLS. I don't think that each and every one of our dipoles fuels a beamline, but in principle they could, and many of them do. And the dipole beamlines are very nice in the sense that you basically get them for free. Once you have a storage ring built and once you have electrons circulating around, you will be getting synchrotron radiation from your dipole magnets. You need the dipoles in order to have a storage ring in the first place, but they also give you beamlines, which is very nice. However, a storage ring does allow you to do a little bit more, and it allows you to extract even more light and get even more beamlines. And this thing that I'm about to talk about now is what sets apart a 3rd generation synchrotron facility from a 2nd generation facility. And that is the introduction of these new devices here called insertion devices, which is a bit of a basic sort of, well, I'll take a step back. I've talked about the cells here, and we can see one cell here. And as I pan over to the side, very quickly, we will see the next cell that repeats. So you can see the 2 dipoles and the flurry of magnets in between and the quadrupoles to either side. And between these 2 cells, one to the left and one to the right, is a straight section. There's some other stuff that I'm about to talk about, but initially there is just one straight section of drift tube where the electrons will be done with this final quadrupole here. They will travel in a simple straight line until they make it to that quadrupole there and eventually that dipole there. And if that was all there was to the story, the electrons just traveling along in a straight drift tube, that wouldn't be terribly exciting, because if the electrons are traveling in a straight line, their trajectory is not changing. And if their trajectory is not changing, they're not producing synchrotron radiation, which is why we're here. So what we do instead is we take this previously empty straight section and insert a device. And the device that we insert is called an insertion device. That is why it's called an insertion device. Physicists are not the greatest at naming things. I will freely admit that. But what an insertion device is you can see it functionally here. We've got this C-shaped support structure, this large support structure that supports some girders. There's a girder above and a girder below. There is also a little detection scheme here with an encoder. And this encoder can measure the physical separation between the 2 girders. And these girders will then be connected to a motor drive that can move the girders in symmetric fashion, such that the upper and lower girders can be moved closer to the electron beam pipe or further away from the electron beam pipe. And upon these girders are many, or rather a row of magnet blocks. So far, when I've been talking about magnets, I've almost exclusively been talking about electromagnets. So coils that are given some current from a power supply, and then the current running through that coil generates a magnetic field. Here with these insertion devices, we're now talking about physical blocks of permanent magnetic material that's, not that different from a fridge magnet, but stronger. And I'll try to get a good angle, maybe one that doesn't involve paperwork taped to the shielding. But, well, there's a decent angle here. where you can see many, many little set screws on each of these little individual pieces of hardware. And each of those little pieces of hardware is a discrete holder for a magnet block. So we can't quite see a good angle of the magnets yet. I'll try to find another angle soon. But looking just head on like this, you can see the many, many magnets, or at least the many, many holders of the magnets. And what would be happening in terms of the actual magnetic field, as we imagine electrons traveling through the pipe. We can see the electron beam pipe right there at the very center. As they're traveling left to right here, beneath this girder of magnets and above that girder of magnets, they will be experiencing, the electrons will be experiencing the magnetic field that is created by this insertion device. And typically what a device will do is, as we go along these magnets, we'll be seeing a north pole, and then a south pole, and then a north pole, and then a south pole in alternating fashion. So if I were to trace out the magnetic field, it'd be doing this sinusoidal sort of pattern all along the length of the insertion device. So this is not so different, and yet quite a bit different from the dipole magnets that we've been seeing, where a dipole magnet is just applying some straight, fixed vertical field that applies a horizontal bend to the beam. Now, we're still seeing a vertically oriented magnetic field, but the magnitude as well as the direction of that field is oscillating periodically throughout the length of this device. So what that ends up doing is this vertical magnetic field will apply steering to the electron beam, except the direction and magnitude of that steering will be sinusoidal. So the electron beam is getting pushed back and forth, back and forth, back and forth by the magnets in this device. So that back and forth pushing causes the electrons to change their direct trajectory quite a lot. They're getting continually pushed back and forth. So the electrons will be doing this undulating or this wiggling sort of motion, and that causes them to produce a tremendous amount of synchrotron radiation. And that synchrotron radiation is, of course, traveling along the initial straight shot trajectory of what was originally this empty straight section. So an insertion device is a very handy tool that we have in order to make use of the electrons and produce a whole lot of synchrotron radiation that then gets shot down a beam line, and that beam of photons can then be used for a new experimental end station. And in this particular case, we can see two of these insertion devices side by side. There is one here on this blue C-shaped support structure, and there's another one on this one next door. And if that were all to the story, we would then have two insertion devices sending two beams of light down the exact same path, which can be nice for some reasons, but it can also be nice to instead have two insertion devices producing light down two distinct beam lines. And from a spatial economy perspective, it's even nicer and more efficient if you can get two beam lines out of a single straight section, which is something that's done really quite frequently here at the light source. Just in the time that I was talking, I walked us over to another straight section. And again, we have two of these devices side by side, but right in the middle, we have a fairly small blue dipole type magnet with a coil above and a coil below and some water cooling lines. And what this magnet right in the very center of the straight section will do is it will apply a very slight kick to the electron beam and change the angle of its trajectory ever so slightly. And there's one of those magnets there. There's an extremely similar sort of magnet over at the other end of the straight section here. And there will be a third one that's largely blocked by my field of view here. You can kind of see the cooling lines there. But there's 3 of these magnets, of these bend magnets, distributed over the length of the straight section. And what these 3 magnets allow us to do is they allow us to pitch the beam at just kind of a very slight positive angle as it's moving through this first insertion device, and then a very slight modest negative angle as it's traveling through this second insertion device. And that angle is really only going to be a fraction of a milliradian, but because we have a very long lever arm, as the photons emerge from this insertion device and from that insertion device and each travel down the respective beam lines, over the course of 10, 12, 14 meters, that small bend angle will allow these 2 beam lines to become spatially separated. And that's the little trick that we play in order to get 2 different beam lines that can allow for 2 different experiments happening at the same time from the same straight section. And when you're limited by time and space and money, that could be a nice tool to have in your toolkit. Now I will continue our walk through the storage ring. We've seen some of the insertion devices along the way, and there are many of these insertion devices at the Canadian Light Source. In fact, as a physicist, a very large amount of my career has been dedicated to the designing and simulating and optimizing and building and measuring and characterizing these different insertion devices, because the basic idea is, of course, to apply that undulating, wiggling sort of kick to the electrons. And in a perfect world, the electrons would arrive at the end of the insertion device and go on their merry way, on position and on angle, kind of shrugging themselves off and then continuing as if the insertion device had not done anything to them. Unfortunately, with real world considerations and the limitations of machining and creating permanent magnet blocks and so on and so forth, it's pretty well unavoidable that an insertion device will have some residual kick, both to the position of the beam, to the angle of the beam, as well as some other kind of higher order beam dynamics considerations that will keep people busy for a long time at the CLS to make sure that the beam stays happy as we continue to add more of these insertion devices or make use of the insertion devices we have. But this device that we're looking at now, we can already tell that it's a little bit different from the ones we've been looking at before, since of course I just went through the process of describing 2 kind of half-length insertion devices that share a straight section for the goal of having 2 beam lines rather than 1. But now that we've arrived at this section of the light source and of the storage ring, instead we just have 1 full-length insertion device, and we have another one down there with that orange structure there. So this is each of these are insertion devices that were designed instead with the priority of maximizing the number of magnets and maximizing the number of north-south bends in order to maximize the raw number of photons that you extract from this ID and send instead down a single beam line, rather than splitting them up and having 2. And that sort of decision is something that will be made quite early on in the design process when you're setting up your machine and when you're deciding what kind of scientific programs you have. Do you want to maximize your flux down a single station, or do you want to have more experiments? These are the sort of things that beamline scientists and accelerator physicists will be in discussion about very early on in a machine's lifespan. So this insertion device here is even more special than that. I will try to get a good angle to really tell the full story here. But what we can end up seeing as I start to zoom in here is we have arrays of magnets both along here. These little yellow stickers are signposts to the start of an array of magnets. So we've got a girder of magnets below here and a girder of magnets above here. And then as we scroll just a little bit to the side, I know it might be a little faint to see, but there is actually a second upper girder of magnets here. So we have magnets both here as well as here, and magnets down here as well as, it might be impossible to see the lower magnets there. But what we're dealing with this particular insertion device is this is a dual insertion device. There are two undulators sharing the same mechanical support structure, and they are just kind of laterally offset between the two. And what can be done is this entire insertion device, this entire, I think it's 14 tons or so, this whole section is on rails. And the whole darn thing can move laterally or perpendicular to the electron beam. And that allows the users at this, this beam line to choose between their two different undulators. The one undulator is focused on delivering higher energy photon light, and the other undulator is focused on delivering lower photon energy light. So the users or the scientists at this beam line really get the advantage of having a full length undulator that's maximizing as much flux as they can possibly get out of their straight section. And they also have the advantage of choosing between a wide range of photon energy, which can influence what sort of samples they might be wanting to image or what sort of experiments they might want to be conducting. So this was a great feat of engineering to have the double undulator onto a single massive support structure. So this is the sort of Cadillac budget option of your beam lines. But even with that said, you can absolutely get a great deal of flux and a great deal of science out of a half-length undulator or a half-length insertion device as well. Now for this next one here, I will also point out, and then I think as we're coming close to 9 o'clock, I will probably start to wrap up and open us up for questions. There might just be one more point I'd like to touch on while we're in the storage ring. But this insertion device here is another interesting and another completely different category of insertion device, because thus far, the different devices that we've been stopping at and looking at, it was relatively easy for me to just zoom in and mouse my cursor over this girder or another girder, and we could physically see the blocks of permanent magnets outside the beam pipe. But now with this device, I can no longer do that. I can zoom in and we can look for magnets, but instead we just see this little enclosure here. And as I continue along the length of the device, that will continue to be the case. Everything is buried. And the reason for that is that this is a so-called in-vacuum insertion device. And by that, I mean the magnets that we were talking about before now are physically enclosed inside of this enclosure. And that allows us to physically position the magnets that much closer to the electron beam. And if the magnets are closer to the electrons, then we can exert a stronger magnetic field out of the same magnets by physically putting them close together, because the overall strength of a magnetic field out of a permanent magnet block, it drops off very, very quickly with distance. So even just by having the physical distance, even if it's 10 millimeters, 12 millimeters of separation, by virtue of having the magnets outside of the vacuum chamber, that actually makes quite a bit of a difference. And being able to instead have the magnets housed within the vacuum chamber is an advantage, but it's also a bit of a complicating factor as well, because now your engineering goals of vacuum tolerance and of having magnets that can physically withstand the radiation from their close proximity to the electron beam, all of these sorts of considerations pile up, and an in-vacuum device becomes operationally more difficult, and there are more kind of risks and potential points of failure with an in-vacuum device, which has, I mean, we're operating well these days, but in the past, we have had some trouble along the way with either one in vacuum device or another. That's just kind of part of the game. So there is one last thing that I would like to point out before I really pause here and start to wrap up. And that is more or less ending how we began. Where in the LINAC, I was pointing out those RF cavities and those accelerating structures. We saw a similar large cavity in the booster ring as the electrons were traveling through the booster ring many, many times. And on each revolution, they were getting an acceleration from the RF cavity in the booster ring. And of course, in the storage ring, as electrons are orbiting around, they will be losing energy by the process of synchrotron radiation. They're shooting off those photons for us for our experiments, which is wonderful, but that costs the electrons energy. They are losing energy by emitting that radiation. And so it is important for us to top them up again and give them an additional accelerating kick such that they can continue around the storage ring for as long as possible. So as I've been walking along here, we can now see the other end of the transfer line. So this is beam coming from the booster into the storage ring. And if we were to follow this transfer line all the way along, eventually we would see more of those kicker magnets, which are used to switch the electron trajectory from the transfer line into the booster ring. But that's more of an aside. The main thing that I wanted to direct us to is this cavity structure here. And I will try this click. All right, that worked out. So what we are looking at here is the RF, or the radio frequency cavity for the storage ring. The cavity itself is very deeply buried, and it's in not something that we can just look at. And the reason that it's buried is because this particular cavity is a superconducting cavity. So there is a tremendous amount of power in that little electric field, that RF power that's bouncing back and forth inside of this cavity. And as before, we are synchronizing the passage of our electron beam pulse with the forward going accelerating part of the RF wave. And because there's so much power in that cavity and we want to minimize the losses as much as we can, that cavity is bathed in liquid helium such that it can be a superconducting cooled cavity. So between the liquid helium bath and the liquid nitrogen, that is, so liquid helium being kind of roughly 3 degrees Kelvin and liquid nitrogen being roughly 70 degrees Kelvin, the liquid nitrogen acts as a kind of insulator that is shielding the liquid helium from room temperature. There's all of this supporting infrastructure and engineering work that needs to be done in order to just build this cavity and satisfy the requirement of applying more acceleration to the electrons so that they can make another loop around the storage ring. So we can see the cavity. We can see another waveguide similar to the ones I was pointing out back in the LINAC. This one's a little bit of a different shape, but it's the same idea of moving RF power from where it is being generated. There's an amplifier elsewhere in the facility to the cavity here. And there's one of our kicker magnets. And that is a lot of the hardware that we will see in order to store our beam, move our electrons around, and ultimately produce synchrotron radiation and send light down beam lines so that users and scientists can go about their experiments. So that's where I'll stop moving the things around and bringing up different talking points. And I'll maybe hand it back over to Juniper, and we can start to wrap up here and take any questions.
Oh, thank you very much there, Cameron. I think that you've done a very admirable job of guiding us around the synchrotron. It's a little bit difficult to do so in a virtual environment. One can easily lose themselves, and some of the angles weren't quite as close as we would like, but I think you've done really a good job of showing us what it would look like if we were present.
Well, thank you, Juniper. I appreciate it.
So I'd like to start off with a virtual round of applause. And I suppose open up the floor here for questions for those who wish to do so. So at this point, you can unmute your microphone if you have a direct question. And if you do not wish to have yourself recorded in asking a question, please inform me either via the chat or in person, and we will try to edit that out when we make the recording available later.
That is all fine. We have a traveling beam of electrons of high energy. Where is the light generated and when? Somewhere I am missing things here.
Yes, I can take this. So you're absolutely right that we have electrons moving around in this accelerator chain. And where the light comes from is because the electrons are relativistic, because they are traveling very, very close to the speed of light, when those electrons have any kind of change in the path of their trajectory, they emit light. And this is a process that factors into basically conservation of energy. If the electrons are changing their trajectory, they need to emit light in order to just balance the equations. And this is a process known as synchrotron radiation. It was discovered many decades ago, almost by accident. There were particle accelerators that were built kind of as colliders and for different scientific applications. And they discovered that when they have these circular machines and an electron or a proton or any other kind of relativistic particle changes its trajectory by going through a bend, it just emits light. So that is something that was discovered quite some time ago, and that led us to the Canadian light source and the synchrotron that we have now, where we have electrons, and by steering those electrons with magnetic fields, by causing them to change their trajectories, they will then emit photons, and we will get light through that interaction.
So correct me if I'm wrong, Cameron, but the so-called first generation synchrotrons were literally ones that were tapping off of existing particle accelerators used for other purposes, as you mentioned. And in some cases, they literally just drilled holes in the the pipe that were used before and welded on another section of pipe and were running an experiment right off the side of something else that was designed for a completely different purpose.
You're absolutely right. Synchrotron radiation was sort of this happy byproduct that ended up being discovered along the way while other physics was being done, and they discovered that it just happened to be this incredibly useful light source, and so here we are with the Canadian light source now.
One man's loss is another man's gain.
You got it.
All right.
Yes, if you talk to other facilities, facilities that aren't light sources. Synchrotron radiation it's more of an inconvenience. It's more of a dirty word, but because we're an electron machine, the synchrotron radiation, like it's why we're all here.
Yes,
So the experiments that are done with light, they are on with the light taken off on different changes of direction, or on bends, and sent somewhere where these the scientists look at different materials to see how whatever they want to see, I guess.
Yeah, you got it. So I'll see if I can find a good angle. You can kind of see it here. It's not the best, but if we go further upstream, here's one of these insertion devices that's causing the electron beam to bend back and forth many, many times, and that's causing the electrons to emit this shower of light. And as the electrons, as they get bent and they stay along this circular path, the photons then get peeled off tangentially. So there'll be another beam, or another pipe rather, beneath this kind of instrumentation that's up top here. So there'll be a pipe that goes along and will then disappear through the shielding wall.
Maybe if you quickly go to the overhead view, that might be easier to see.
I think that is a good idea. So here's the storage ring tunnel that we were walking along just now. And there will be this tangential line, and this will be where the photons go. The photons and the light exit the storage ring and go towards an end station, whereas the electrons continue to orbit around the storage ring.
Yeah, okay, thank you.
Hi, Caroline. I have a question. We usually characterize the generation of the synchrotron facility by the generation of the insertion device. Like in the third generation, we use the bending magnets or undulator. But can you correct me if I'm wrong? Because if in my knowledge, the third generation, it usually consists of just a bending magnets. But during the tour, I see also the undulator, and also there's a couple, what do you call that, the
wigglers,
the wiggler. Yeah. So is that wrong? Is that correct if I say that the third generation only consists of the bending magnets?
I think that's where you've misstepped. So I'll give a high-level summary on the different generations of synchrotron light sources. As Juniper already mentioned, the first generation machines were built for entirely different purposes, and then synchrotron radiation was discovered and was made use of parasitically. So that was the first generation of machines. Second generation synchrotrons were the first machines that were designed with the express purpose of making use of synchrotron radiation. Then the third generation came along, which is what we are. We are a third generation machine. And what sets a third generation apart from a second generation is the insertion devices, so the undulators and wigglers. So a second generation machine would only have dipole bend magnets for its beamlines, and a third generation machine has these undulators and wigglers. It also has the dipole magnets, but there will be both dipole or bend magnet beamlines as well as insertion device or ID beamlines at the CLS. We have both, but the insertion devices are more or less an upgrade compared to, or rather a development compared to just having dipoles.
Okay, yeah, I got it. Thanks.
Okay, yep, no problem.
Well, if no one else is jumping in with a question here, I actually have a question.
Sure.
When you were talking about the in-vacuum wiggler there, you have these girders that are able to move within the vacuum environment. what is used to lubricate this system that will not result in off-gassing?
That's a very good question. If we had one of our mechanical engineers on the call, I would be able to give you a better
Fair
answer.
enough.
But something that I will add is dealing with the magnetic forces of these devices and these girders is a very important consideration, especially for the in-vacuum devices, because the magnets are physically closer. So you can be dealing with upwards of 10 kilonewtons of force from one girder towards another. So often you will see balancing springs that are kind of off to the left and the right of the magnets. And these springs are kind of part of helping to just account for the forces.
Yes, I'm trying to recall that the large undulator that you showed there, the QMSC, memory serves me, the magnets, when they're placed on, are actually sufficient enough to actually cause those two horizontal girders, sets of girders, to actually flex slightly enough that it threw all the calculations off.
Let's see. They flex enough that we had to look at it and calculate it in the early design stages of predicting how much will things flex, how much will that have an effect on the beamline. So it's definitely something that we had to think about and look at. I don't quite recall it throwing us off in the way that you're describing, but
I could have, I might have had an exaggerated recollection of
well, I mean, a similar anecdote is with the one of the newest insertion devices that we did for the VLS PGM beamline. That is a relatively high strength, beefy kind of device, because the physical magnets are quite large, so the forces that they exert is quite large, and that ended up giving us some unexpected trouble. And at the assembly stage, when we were putting those magnets into those holders and those holders onto those girders, the forces were so large that, I mean, right off the hop, they're vastly too strong for a human to deal with. You need jigs and tooling to lay the magnets onto the girder. But the forces were even too strong for our jigs and tooling. And one of our jigs ended up kind of warping, and you know, the railings were popping off because it couldn't deal with the forces. So we had to take a step back and re-engineer our tooling. So there's a lot of interesting design challenges that come up across the board when we're dealing with these insertion devices.
Well, maybe I'll ask another broader question here then, to give others a chance to think of some more questions for you. As an engineering physicist, how far do you see yourself from most of the rest of engineering?
Oh, wow. Let's see, how far do I see myself? I wouldn't say that far, because like a lot of the things that I need to worry about tends to be things we can't see with the human eye. Like I'm doing design and simulation calculations on magnetic fields and forces and what a magnet might do to the electron beam. But it's pretty regular that I will go down the hallway and have a conversation with the mechanical engineering group or with the electrical engineering group, because so many of the projects at the light source are so cross-discipline. It's pretty easy and pretty regular to get us into the same room and talking the same language.
Fair enough. Again, you know, many of the things that I deal with are also not things that anyone can see. They're sort of abstract concepts of data and or signals, and you know, current and voltage traveling down various wires. But yeah, at the end of the day, we're always relating it back, to general engineering principles and things that most engineers would recognize, even though it may seem a little esoteric to you know, the untrained eye or at first blush.
Yep, you need your drawings, you need your design, and when your simulations make contact with the real world, things might go a little bit unexpected, but that's where a lot of the interesting discovery happens, and that's where you find your sources of error and where you kind of reiterate on your approach as you need to, and engineer your solution.
All right. Are there any more questions here for Cameron? Well, if not, I'd like everyone to give Cameron another virtual round of applause.
Thank you, Cameron.
Thank you, everyone.
Great presentation. Thanks a lot.
Thank you. Yes, thank you everyone for coming and for attending. It was I've given quite a few tours over the years, but none of them recently and none of them virtually. So this was a fun new experience for me.
Yes, this is a bit of an experiment here. We were seeing what we could do. But so again, thank you, Cameron, very much. And it appears that we have reached the end of this tour. So I bid you all a good night and Godspeed.